Hi everyone. RAG, short for Retrieval Augmented Generation. Let us see what it means. Have you ever wondered how tools like ChatGPT can answer questions from your own PDF files, company documents, or even thousands of pages of technical manuals? The answer is a powerful technique called RAG. Whether you want to build a document chatbot, an AI assistant for your company, a customer support bot, or simply understand how today's AI applications work, this video will give you the foundation you need. How RAG enables AI to answer questions using your own knowledge instead of relying only on what it learned during training. So, let's get started. Now that we know what RAG is, let's first understand the problem it solves. I'm here on ChatGPT. Let's start with a simple question. Who is the CEO of Microsoft? As expected, the AI answers correctly because this is public information that it already knows. Now let's try something different. I have an employee handbook PDF on my computer. Let's ask the AI a question about it. According to my employee handbook, how many annual leave days does an employee receive? Notice that the AI can't answer this question. It either says it doesn't have access to my employee handbook or it asks me to upload the document because large language models don't automatically know what's stored on your computer. They only know the information they were trained on and they cannot read your local files unless you provide them. Let's try another example. I have another PDF containing our company's work from home policy. I'll ask what are the eligibility requirements for working from home. Again, the AI has no idea because this information exists only inside my document. Of course, I could upload the PDF every single time I ask a question. But imagine having hundreds or even thousands of documents. How can we allow an AI model to automatically search through our documents? That's exactly the problem RAG solves. Let's see how that works. Let's go a little deep with the example which we were trying just now on the screen. Imagine we have our company documents. These could be PDF files, Word documents, Excel files, user manuals, HR policies, or even research papers. Let's say one of these documents contains the company's leave policy. Now, over here, this box represents a smart search system. Unlike a normal keyword search, this search understands the meaning of your question. Now let's add one more box. This is our AI model, ChatGPT, Claude, Gemini, Groq, or any other large language model. Now let's see what happens when a user asks a question. Say the user asks, how many annual leave days does an employee receive? What happens first? Does the AI immediately answer? No, instead the question is first sent to the search system. The search system looks through all of our documents and finds the page that talks about annual leave. Instead of sending every document to the AI, it sends only the most relevant information, maybe just one paragraph or two or three small sections. Now the AI finally has the information it needs. In a way, it reads the right information at the right time before answering. That's exactly why it's called retrieval augmented generation. Retrieval means finding the relevant information from your documents. Augmented means adding that information to the AI's prompt. Generation means the AI uses that information to generate the final answer. That's exactly what makes RAG so powerful. At first glance, this diagram may look complicated, but don't worry. By the end of the next few minutes, every box will make sense. Before users can ask questions, we first need to prepare our documents. The first step is called parsing. Parsing simply means extracting the text from those documents. Notice this box called splitting into small chunks. Each chunk might contain just a few paragraphs. Next comes the embedding model. You can think of an embedding as a mathematical fingerprint for a piece of text. After creating embeddings, we store them in a vector database. Now we have an embedding for the user's question. The system compares that embedding with all the embeddings stored inside the vector database. This process is called Similarity Search. After finding the most relevant chunks, we move to the next stage called augmentation. Finally, we reach the last stage. The augmented query is sent to the large language model. And that's the complete RAG workflow. Now that we understand how RAG works, let's build one from scratch using Python. I've already opened Visual Studio Code. The first thing I'm going to do is create a new folder called RAG tutorial. Inside this folder, I'll create a Python file called main.py. This is where we'll write our RAG application. Before installing the required libraries, let's create a virtual environment, open the terminal and run python hyphen mvenv. Now let's activate it. If you're using Windows, run this command. Once activated, you should see venv in your terminal. Now let's install all the libraries we'll need. I'll install them using a single command. Let's quickly understand what each of these packages does. LangChain helps us build the entire RAG pipeline. LangChain community provides document loaders and vector database integrations. LangChain Groq allows us to connect directly to Groq's fast inference API. PyPDF reads text from PDF documents. Sentence Transformers creates embeddings for our documents. ChromaDB stores those embeddings in a vector database. Python totem loads our API key from a AM file. Once the installation finishes, we are ready to start coding. Inside the project folder, create a new file called NEAV. Inside that file, paste your API key like this, which is much safer than writing your API key directly inside your Python code. At this point, our project looks like this: RAG tutorial BENV, main.pyenv. Everything is now ready to begin building the RAG pipeline step by step. Now that our project is ready, the first step in building any RAG application is to load our documents. In my project, I've already created a folder called Documents, and inside it, I've placed an employee handbook PDF. Of course, you can use any PDF you like: company policies, product manuals, research papers, invoices, or even your own notes. Our goal in this step is simply to read the contents of this PDF into our Python application. Let's start by importing PyPDF loader from LangChain. Now I'll create a loader by passing the path to my PDF file. Next, I'll call the load method. This method reads the PDF, extracts the text, and returns the contents as a collection of document objects before moving any further. Let's make sure everything is working correctly. I'll print the total number of pages that were loaded, then I'll print the contents of the very first page. Perfect. You can see that the PDF has been loaded successfully. It found 34 pages, and here is the complete text from the first page. So at this point, we've successfully extracted the text from our PDF. But there's something interesting happening behind the scenes. What exactly is this document's variable? Is it just one large block of text, or is it something else? Let's find out. I'm going to modify the program slightly. This time, instead of printing just the first page, let's inspect what LangChain actually returned. First, I'll print the type of the document's variable. Then I'll print the type of the first item inside that list. Finally, I'll loop through every document and print a small preview from each page. Now let's run it again. Notice the first output, the documents variable, is actually a Python list, and each item inside that list is a document object. That means LangChain doesn't treat the entire PDF as one giant piece of text. Instead, every page becomes its own document object. Now, as we scroll through the output, you can see a preview of every page in the PDF: page 1, page 2, page 3, and so on. This makes it much easier for us to process the document in the next steps. At this point, you might be wondering, why can't we simply use these pages directly? The answer is that a single page can contain a lot of information. If someone asks a question like, how many annual leave days do employees receive? We don't want to send the entire page or even the entire document to the AI model. That would be inefficient, slower, and more expensive. Instead, we split the document into much smaller pieces called chunks. Each chunk contains only a small portion of the document, making it much easier to search for relevant information later. Let's see how to do that. First, I'll import recursive character text splitter from LangChain. This class helps us split large documents into smaller chunks while keeping some overlap between consecutive chunks. The overlap is important because it prevents information from being lost when a sentence spans across two chunks. Now let's create a text splitter. I am setting the chunk size to 500 characters and the chunk overlap to 100 characters. These are good values for a beginner project. Next, I'll call the split documents method and pass the documents we loaded earlier. This returns a new list containing all the chunks. Let's print the total number of chunks that were created. And finally, let's display the first few chunks so we can see what they look like. Perfect. Notice that instead of large pages, we now have much smaller pieces of text. Each chunk is easier to search and process. In the next section, we'll convert each of these chunks into embeddings, which are numerical representations that allow the computer to search by meaning instead of just matching keywords. So far, we've loaded our employee handbook PDF and split it into smaller chunks. A computer doesn't understand text the way humans do, but a computer simply sees different words. So, how do we make a computer understand meaning instead of just matching keywords? That's exactly where embeddings come in. LangChain makes it very easy. First, I'll import Hugging Face embeddings. This class will automatically generate embeddings for every chunk in our document. I'm going to use the model called AllMiniLM L6v2. We need somewhere to store those embeddings. That's where ChromaDB comes in. You can think of ChromaDB as a special kind of database. Instead of storing text, it's storing the meaning of that text. As soon as we run this code, LangChain automatically creates embeddings for every chunk and stores them inside ChromaDB. Let's run the program. Our employee handbook has now been converted into embeddings and stored inside a vector database. We don't actually see the embeddings because they are just long lists of numbers, but they are now ready to be searched. In the next section, we'll ask real questions like how many annual leave days do employees receive, and watch ChromaDB retrieve the most relevant information before sending it to Groq for the final answer. So far, we've stored all of our document chunks inside ChromaDB. But how do we actually use them? Let's say a user asks a question, how many annual leave days do employees receive? The first thing RAG does is not send this question to the language model. Instead, it searches the vector database. Remember, every document chunk was converted into an embedding and stored inside ChromaDB. Now, our user's question is also converted into an embedding. ChromaDB compares that embedding against every stored embedding and finds the chunks with the most similar meaning. This process is called Similarity Search. The great thing is that it doesn't rely on exact keywords. Even if the document says annual leave and the user asks about vacation days, the embedding model understands that both phrases have a similar meaning. Let's see this in action. Instead of asking Grok, I'm going to ask ChromaDB directly. I'll write the question, how many annual leave days do employees receive? Here in the code, we are using similarity search. Then I'll ask ChromaDB to return the three most relevant chunks and printing the results. That's all we need. Let's run the program. Look at the results. These aren't random chunks. ChromaDB has found the sections of the employee handbook that are most relevant to our question. This is exactly what we wanted. At this stage, we got results like our company observes the following holidays: New Year's Day, Independence Day, so on till Christmas Day. We simply found the right information. In the final step, we'll send these retrieved chunks along with the user's question to Grok, and it will generate clear, natural language answer based on the information we retrieved. Let's move to the final section. We want the AI to read the relevant information and generate a natural, human friendly answer. This is where Grok comes into the picture. Grok is providing us with the large language model or LLM. Before we run the program, let's quickly understand what this code is doing. First, I am importing chatgrok from LangChain. Next, I am importing load.env. This simply loads all the variables stored inside our .env file. Then we read our API key. Now Let's look at the next section. This is where we create our language model. We are choosing the Llama 3.370B versatile model because it's fast and works well for RAG applications. From this point onwards, whenever we call LM in voice, our request will be sent to Groq and Groq will return the generated response. Now we come to probably the most important part of this entire application, the prompt. This is simply a Python multi-line string. The F before the triple quotes means it's an F string. An F string allows us to insert Python variables directly into the text using curly braces. Notice something important. We are not sending the entire employee handbook. We are only sending the few chunks that ChromaDB found to be relevant. That's what makes RAG fast and efficient. Notice what happened. Groq didn't search our employee handbook. It simply received the relevant sections from ChromaDB and generated a clear, natural language answer. The language model generates the answer, and together they create an AI assistant that can answer questions using your own documents. And we received the final answer. Employees are entitled to 20 days of annual leave. And that's it. We've built a complete retrieval augmented generation application from scratch. And that's it. We've successfully built a complete RAG application from scratch. We loaded a PDF, split it into chunks, created embeddings, stored them in a vector database, retrieved the most relevant information, and finally used Groq to generate an answer based on our own documents. I hope this video helped you understand how RAG works and gave you a solid starting point to build your own AI powered applications. If you found this video helpful or if there is another AI tool you'd like me to cover next, let me know in the comments which feature impressed you the most. If you enjoyed this video, don't forget to like the video and subscribe for more practical AI videos. Thanks for watching and I'll see you in the next one.